So after looking at the past few slides, hopefully you noticed a few things. First of all, that's the Earth rotating under these bulges of water. These bulges caused by the gravitational attraction and by inertia. And as the Earth moves around underneath or rotates underneath these water bulges, we experience high and low tides on the planet. Times when the duck was floating in water and times when the duck was stuck on dry land. The other thing you might have noticed is that that time period between a period of low tide and high tide was not 6 hours exactly, but it was usually offset by about 6 hours, initially 6 hours and roughly about 13 minutes. Now, we think about the length of a day on the Earth. We know that it's 24 hours long, and we can break that up into 4 segments of 6 hours each. But if we look here at this example that we just used, we see that one complete rotation of the Earth is 24 hours, but from T1 to T5, it was 24 hours and 50 minutes. And why is that? Well, it's because the moon revolves around the Earth in the same direction. So the Earth is rotating in an eastward direction. The moon is revolving in the exact same direction as well. And what this means is it takes the Earth 50 extra minutes every day to basically catch up with the moon. A lunar day is the length of time of day when the moon is the highest in the sky, and the next time of day when the moon is the highest again. And we see that the lunar day and solar days, or the days that it takes the Earth to revolve once around its axis, are not exactly the same. Day, as we experience, is 24 hours. The lunar day is 24 hours and 50 minutes. And that's why we see that offset in times as the Earth rotates underneath that bulge of water. The bulges are created in part by the moon, which is moving at a slightly different rate, and the Earth is trying to play catch up all the time. So we get this lag of times, this sort of difference in times. And this is why when you look, as we'll see in a second, at time or tidal charts for different locations in the planet, you'll see that the tide does not always occur at the exact same time every day. So we can't say the high tide is going to be at 12 today, 12 tomorrow, 12 on Saturday, and so on. We always see that high tide is always offset from one day to the next, and low tide's the same thing. So this slide then just summarizes what I said in the previous slide. Once again, one complete rotation of the Earth is 24 hours longer for a lunar day, 24 hours and 50 minutes. It takes an extra 50 minutes for the Earth to catch up to the moon, and the length of a lunar day. And this is why we see that it takes roughly 6 hours and 12 and a half to 13 minutes to go from high tide to low tide in an area. Generally, we'll see that there's exceptions to this depending on what the coastlines are like, but typically we have that lag of time, 6 hours and 12 and a half minutes from low tide to high tide. And for anyone out there that still wants to kind of take a look at it and go, okay, this is what's going on, this final slide just once again illustrates what I've been talking about in the last two slides. We start off on the left-hand side of the image at, let's say, time 0, and you can see the rotation of the moon around the Earth, as well as the rotation of the Earth, and that it shows that it takes an extra 50 minutes for the Earth to catch up every day. We have a solar day, which is much shorter, or 50 minutes shorter than the lunar day. So that time lag between the length of a lunar day and the length of a solar day means that we see something like this. What we see in the lower part of the slide right here, where we have times and heights for high and low tides, we'll see, and this is from back in March of 2019, we'll see that going from a Friday to a Saturday all the way through to a Monday, that the time of day at which high tide occurs and low tide occurs changes every day, and is always usually offset by about an hour and 15 minutes or so. So if you look, for example, at low tide at 1:17 a.m. on the 29th, we go one day over to Saturday, and we see that low tide at that time is at 2:25 in the morning. So it typically offsets, as I said, once again, by about an hour and a half every day, or an hour and 15 minutes, I should say, every day. What we're seeing here is something that we call a semi-diurnal tide. This is when we have 2 high tides and 2 low tides of approximately equal size on every lunar day. So twice a day, if we're here, let's say in Wolfville, we rotate as the Earth revolves or rotates around its axis. We rotate underneath 2 of those bulges of water, the gravitational bulge and the inertial bulge. And then there's times twice a day when we rotate out from underneath those bulges. And this is really typical of the Atlantic coast. So it seems a little counterintuitive, but semi-diurnal tides means that we have two high, two low tides of approximately equal size every lunar day. So every 24 hours and 50 minutes. So semi-diurnal tides are not the only tide type that we can have, the only thing that, tide frequency that we can have. We also find that we have diurnal tides and mixed semi-diurnal tides. So diurnal tides are very typical of places, coastlines that we might find along the Gulf of Mexico. These are locations where we only experience one high tide a day and one low tide every lunar day. This is usually controlled by the shape of the basin. If you think once again of the Gulf of Mexico, sort of down along the southern part of the United States, it's a fairly enclosed basin, smaller body of water. Because of the basin shape, we experience only one low and one high tide every day. We also have locations where you have mixed semi-diurnal tides. So this means once again that we have two high and two low tides every lunar day, but the difference between high tides, so two high tides a day, is quite significant. So we have sort of like a high tide and then a high tide, and with low tides, sort of a low tide and then a really low tide. And this is common along the Pacific coast. This map here then shows sort of where we can expect semi-diurnal tides, which show up in green, diurnal tides, which show up in yellow, and then these mixed semi-diurnal tides that show up in red. And this is where we might experience them around the planet. We see that twice daily tides dominate. We see that we get a lot of mixed tides, especially around, as well as diurnal tides around the Pacific Basin. That's because we have very complex tidal patterns along there. Complex circulation patterns, a number of different things are going on there, and that's why we sometimes see very complex tides. For anyone who's wondering, you won't see a map like this on a exam and me asking you, okay, show where all the mixed tides are, show where all the semi-diurnal tides are, show where all the diurnal tides are. What I'm more concerned about with this particular image here is that it just gives you a sense of where we can experience different types of tides throughout the planet. So far, we've been focusing on what happens between the moon and the earth and the role that the moon plays, especially the gravitational attraction between the water on the earth and the moon in generating tides. But now we're going to throw the sun into the mix as well. So remember, the sun is 27 million times more massive than the moon. It does play a role, but it's only about 46% of that of the moon's. But still, we'll see that the sun can have a major influence sometimes on what is going on in terms of tides on the planet. Remember, as it says in the slide there, that the Earth-Moon system is orbiting around the sun. So we'll see that on a yearly basis, the position of these three celestial bodies changes. And in fact, not only on a yearly basis, but we can see that bi-weekly and monthly as well, these three celestial bodies change position relative to each other, and this can have a dramatic effect on the tides. So if you look at this diagram here, you'll see words like aphelion, perigee, apogee, perihelion. I don't really expect you to remember this, but what I want you to take away from this slide is that there's times of the year where, due to how the orbit of the moon-Earth system around the sun is, that we'll be closer to the sun, and then there's times of the year where we might be further away from the sun. And all of these are going to play a role in how tides are generated and the height of tides sometimes, what we call the tidal range, is on the planet on sometimes a monthly basis or sometimes on a yearly basis. One of the things that can occur is that when the Earth is closest to the sun, this is at the thing called perihelion, what we'll see is that tidal ranges can be enhanced, and then other times when the Earth is furthest from the sun, what we see is that tidal ranges will be reduced. It doesn't mean that they go down to nothing, but they might be lower than they are on average. What role then does the sun play? We talked in the previous slide how when we're closer to the sun, tides might be higher. When we're further from the sun, tides might be a little bit lower. And this is on average, or lower or higher than what sort of the average tidal range is. But even on a monthly basis, we can see that there are changes on what the normal average sort of day-to-day tidal range is. And these are what we refer to as neap and spring tides. The first thing we need to say right here is that spring tides does not refer to tides that only occur in the spring season. Spring tides is a term that means that the water appears to spring forth. The springing forth of water is how it's often described in textbooks. What you need to know about spring tide is the tides of maximum range. This is when we'll see tides at their absolute highest. And they occur every 2 weeks when the moon is either in a new or full moon phase. So if you live in an area that experiences tides, for example, where Acadia is here in Wolfville, when it's a full moon out, you can see that at high tide, the water level is much higher than it is at other times during the month. And this is because if you look at our little diagram here underneath the text on the slide, you'll see that we have the Earth-Moon system. This is usually when they're all in alignment. For example, when we have the Earth, Moon, and Sun, as we see on the right-hand side of the slide, well, not only do we have the gravitational attraction of the moon, but we also have the gravitational attraction of the sun enhancing the moon's gravitational attraction. So that's going to pull that bulge of water out even further. On the left-hand side, and I apologize for this being a little bit backwards, but we have the moon, earth, and the sun. So once again, we have that gravitational attraction between the moon and the earth, creating that gravitational bulge. But now that inertial bulge, that is being enhanced now by the gravitational attraction of the sun. So on that side of the earth, then, as the earth rotates underneath the bulges of water, we'll experience higher than normal tides as well. Now, neap tides are when we have the opposite situation. This occurs when we have tides of minimal range, so that low tide might be lower than normal. And once again, it's a monthly occurrence. We see it occurred every 2 weeks when the moon is in what we call its first quarter or third quarter phase. What this means is what we see here. The moon and the earth and the sun now are at right angles to each other. And this has the net effect of causing minimal tidal ranges, lower tidal ranges. What basically happens now is we see the sun and the moon directly opposing itself. We have opposing gravitational forces between them, and that leads to lower than normal or lower than average tides during these periods of the month. So spring tides are these tides of maximum range that occur every 2 weeks. And they can be of concern, especially in coastal communities. I know this is an issue in places like Victoria, BC, and places like Miami, Florida. And this is what you see is you'll have this sort of high level of water. It results in coastal flooding if this is a time as well when we might have storm activity. For example, a storm surge is coming on shore. There's hurricanes in the area. This can actually increase the fact that we have normal and high levels of water, and then we have a storm coming through. It can actually increase the level of water and cause quite often some quite extensive coastal flooding. So spring tides, they're sometimes referred to as king tides as well, can be of concern to city officials, people, anyone who sort of lives or works around a coastal community. Okay, so we have times of high tide and times of low tides. This brings us to the concept of tidal range. And what a tidal range is, it's the vertical difference between consecutive high and low tides. So if you have a high tide in the morning and a low tide in the afternoon, what is that difference between them? And that would give your tidal range. So the tidal range is constantly changing. You can't say, oh, the tidal range is going to be 12.2 meters here forever and ever. It's going to change from day to day to day. Now we can have average tidal ranges, and this is what we see in this diagram here. It refers to mean low water, mean low water, and mean is just another way of saying average. So these are the average ranges that we see. Once again, I have this diagram up here just so you know, be aware of what different terms are, but I'm not going to ask you what MLLW or MHHW means on an exam. What I'm more concerned about is that you know what a tidal range is and the fact that it's that vertical difference between consecutive high and low tides. We are able to classify tidal ranges then. And we have different types of tidal ranges, sort of three main broad classifications. We can have macro tidal. This is where that tidal range, that difference between low tide and high tide, is greater than 4 meters. And that's shown by the really dark colored images on that map, or areas on the map. We then have the mesotidal. This is 2 to 4 meters. This is shown by sort of that medium gray coloration on the map. And then finally we have microtidal. These are tidal ranges less than 2 meters. This is very typical of what we see like along islands in the open ocean. Once again, it all depends on what the coastline is like and what is going on along that coastline, whether or not we're going to have a microtidal range or a macrotidal range. As you can see, it's variable throughout the planet. One area, if you can kind of pick it out, of note is Nova Scotia, where Acadia is. And here we experience some of the highest or greatest tidal ranges on the planet. Tidal ranges in the Bay of Fundy, especially in what we call the minus basin in the Bay of Fundy, can reach up to 16 meters, so roughly 53 feet difference between when low tide is and when high tide is. So this definitely is a macrotidal range. As the tide comes in then, and we reach high tides, and as the tide goes out and reach low tides, we'll see that there's areas along the coastline that are exposed. And in fact, we can sort of divide the coastline into 3 broad areas depending on what the water level is or where the water level is in relation to it. So we have on this diagram here, starting on the left-hand side, so right along the beach, is something called the supratidal zone. And this is an area that is usually going to be above water, even at high, or it's only when we have really high tides, for example, like spring tides, that we might see this zone covered by water. Then we have this vast area called the intertidal area. And this is probably the most interesting area in terms of tides. This is where we see during periods of low tide, it's exposed to the weather, to the elements. And then when the tide comes in and we're under high tide, then this area is covered by water. Finally, we have the subtidal, and this is the area that's constantly going to be underwater, no matter what time of day it is, where we are in the tidal cycle. Are we in a high tide or a low tide period at the time? It might be just when we have those neap tides that a little bit of the upper portion of the subtidal zone might be exposed. But as I said, we can break the areas down into the subtidal, intertidal, and supratidal. And in fact, we'll talk about life in the intertidal zone in a subsequent lecture on biology and the oceans. This is an image of very similar to what we saw in the previous slide. So once again, tide is low here. We see this vast expanse of intertidal zone, which is usually muddy sediments, especially here on the East Coast, but in other parts of the world, it can be rocky coastlines. We see that it's exposed, but cutting across this particular image is something that we call the tidal creek. So this is a channel that's been cut into that sediment, that soft, muddy, mucky, mushy sediment, that as the tide goes out, water flows out through the tidal creek into the deeper part of the ocean or offshore. And then as the tide comes in, water will flow back in up along this tidal creek and eventually flooding the intertidal zone there as well. So the tidal creek will experience currents in one direction and another direction twice every lunar day. And what we have then is we have what we call the flood current and the ebb current. So the flood current is when water is moving towards the land. The name says it right there, flood. We're flooding the land. We're flooding the intertidal zone. As the earth rotates, we move underneath that bulge of water and the land starts to flood. Water starts to cover that intertidal zone as well. And that's indicated by the green on the diagram here on the figure. Then, as the tide goes out, we have the ebb current. So that's water moving offshore. We have falling water levels. And this is indicated by the red arrow that we see in the image. We also see that during this tidal cycle, so when we have flood currents bringing water in, ebb currents bringing water offshore, that we do have times of slack water. And this is a period when there's no movement of water either towards land or offshore. Everything is just sort of sitting there. And you can see it once again on this diagram here, this graph, that we have 2 episodes of slack water, low slack water during the day, and 2 episodes of high slack water. So we have both high slack water and low slack water periods. And there's no movement of water either one way or the other within that tidal creek. It's just all sitting there. There are locations on the planet along coastlines where we see a very interesting phenomena. And this is one such example. This is along the coast of BC in a place called Skookumchuck Narrows. And what we have here, we have 2 high tides, 2 low tides a day. The tide comes in, the tide comes out. We have that flood current and that ebb current. But at this location here, what happens is that this tidal current, which is moving very quickly, all of a sudden gets squeezed through a very narrow passage. It's going from a very large area, and all of a sudden this water that's coming in has to move through a very narrow passage. And what this results in is something that we call tidal rapids. Water moving within this on either the flood current or the ebb current can travel at speeds of greater than 31, 32 kilometers an hour. And we can actually see the difference in height of water from one side of the rapids to the other will often exceed 2 meters in height. So it's quite an impressive phenomena. As I said, we're not going to see this at every location where we have tides coming in, but it's a unique phenomenon that's restricted to certain areas along coastlines. Some people consider this to be the fastest moving tidal rapids in the world, but there are other locations that might, beg to differ and say, no, we have the fastest moving tidal rapids. Another phenomena that might occur if you are on the East Coast and you're in Nova Scotia, this is one that you might be very familiar with. There's other locations, Trinidad Arm up in Alaska, the Severn Estuary in England, locations within China, but we see this thing called the tidal bore. And this sometimes is referred to as a tidal wave, and even though I said you can't call tsunamis tidal waves, I'm totally cool with you referring to this as a tidal wave. What happens as the flood tide comes in, as that incoming tide is coming in, it will travel up a river or a narrow bay. And what happens is we're going once again from a wider area of water into that water being basically funneled into an increasingly narrower and narrower area. In this case here, what happens is it creates a wave, what we call a standing wave. So a wave that kind of maintains position. It's not breaking, it's not falling in the sense that we traditionally think of waves as behaving. But this wave, or it could be multiple waves, will travel up the river against the direction of that river's current. So for example, a river commonly wants to flow out to the ocean. This tidal bore will travel up the river. For example, the Shubenacadie River here in Nova Scotia will travel up the river against the river's direction of flow, against the river's current. And this results in the creation of the standing wave, which you can see in the image right here. So the tidal bore, as I said, is a pretty unique phenomenon. Once again, we don't find it occurring everywhere in the world wherever we have a tide, but we do find it occurring in areas where the settings are just right. So here, once again, in Nova Scotia, you can see the Google Earth image at the upper right. We have the Shubenacadie River being fed out of the off of the Bay of Fundy. And we can see that it progressively gets narrower and narrower and narrower. So we get this steep wave that travels up the stream, upstream as opposed to traveling downstream, creating this breaking wave. The people below the text in the slide here, you can see they're standing in this nice dry area of sand. About 10 minutes later now, that's completely covered by water, at least about 6 feet of water or so. And it's going to move towards land very quickly. So this actually is used as a tourist attraction. People will come up, they'll ride in rubber rafts with engines, and they'll basically do what we know as tidal boat rafting, sort of the tidal equivalent of whitewater rafting, and ride this wave. And quite often you get waves that sometimes might be, 2, 3, 4, 5 meters high. In other parts of the world, this actually occurs in Nova Scotia, in New Brunswick as well. People will often surf the tidal bore as it comes in. And the next slide, what you'll see is links to a couple of videos that show you examples of the tidal bore and what happens within tidal bores.